All right, so this video is prepared to go over section 8.2 from chapter 8, and has the main goals here are to learn about trigonometric form, or called the polar form, of complex numbers. This will help you tremendously in science to understand the vector representation, and especially when you decompose a vector that is in an xy plane or even xyz plane in components for each axis. So then you're going to learn about converting between standard or regular form and trigonometric or polar form. And one fun application that has to do with complex numbers, it's called fractals. So let's go ahead and start this. And one important thing is to understand how we represent a vector here. So a complex number that you can write in a form of a plus ib, or bi, has a real part, which is this a right here, and has an imaginary part, which is that b right there. So essentially, instead of having an x and y plane, we call it a complex plane, where on the x-axis, we're going to represent the a part of the number, and on the y-axis, we're going to represent the imaginary part of the number, which is b in this case. So if we are looking at the number 2 minus 3i, and we identify that a is 2 and b is negative 3, then we can come up and look at this. And as you said, a is 2, it is your real part, and then b is negative 3, and you find an intersection between them. Hence, you get the vector, which is situated from origin and points out to the end of the point that we found. So essentially, if we have to fill out this information here, when you graph it, a complex number, in this case was 2 minus 3a, you modify the coordinate system by calling the horizontal axis the real axis. Real axis. And then the vertical axis, we call it the imaginary axis. Then the complex number can be graphed in this so-called complex plane. And that's represented in depicted in a picture. Now, each complex number that has the form a plus bi can determine a unique position of a vector. And then you're going to have an angle that it's common to this, right? In this case, you're going to look at an angle theta. In here is below the x-axis for this particular vector. So always the initial point, remember, is in the origin. And then the end point has the coordinates a, b. Right? So this point right here, P, I'm going to write it as coordinates a, b. In our case, was 2 and negative 3. I think that should be specified in here. All right. So now, essentially, the geometric representation is the reason that a plus bi is called a rectangular form. Let me highlight this. So it's the rectangular form. Of a complex number. And this rectangular form, many people call it just a standard form. So please, every time I'm referring to rectangular or standard, they mean the same thing. So now, graphically, when you put two complex numbers together, you're going to have two vectors. And when you add together the vectors, I don't know how much you remember from geometry, but you can use the parallelogram method or tip-to-tail method. There's very many methods to do that. That vector, the new vector, when you add them, it's called a resultant. Essentially, what is the result of adding two vectors or subtracting two vectors? When you subtract two vectors, you can write any subtraction as a addition. For example, if I say 2 minus 3, I can sure write that as 2 plus negative 3. So the point is, you can only talk about addition, make it easy, and then negative 3 means that the vector has the opposite direction. So let's do an example here. So in the first example, you have two vectors, and they are 2 plus 3i, and the other one's negative 4 plus 2i. And you are asked to graph both of these and then find a resultant. So they want you to do this graphically. That means we're going to focus on each one, which one is a plus bi. Well, for the first one, a and b becomes, or is, 2 and 3. So I know that if I go on the x-axis, which is the real part, so that's where you put your a, and on the y-axis is the imaginary part, and that's nothing else but representing your b, then I can go at coordinates 2 and 3. I'm going to zoom in right now. So at 2 and 3, I'm going to find the end of that vector. So I'm going to draw it. I'm going to try to be as precise as I can. So here is the coordinates here are 2 and 3. So that was my first vector. That represents the number 2 plus 3i. Okay, so I'm going to write right next to it 2 plus 3i. Okay, now the next vector, let's change colors on that one, has the coordinates a, b, if you look, is negative 4 and 2. So let's go ahead and find that one. So I'm going to go to x is negative 4, which is right there, and then 2. The intersection between them will define the end of your vector. Starting from origin, you're going to draw that vector and put the end of it. So this one has the coordinates negative 4 and 2. Represents the vector negative 4 plus 2i. So now the question is, how do you find the resultant? So the resultant of a combination of vectors is if you draw a parallelogram using the size that you already have. So literally, if I am trying to draw a line that is parallel to, let's say I'm at this end, a negative 4 and 2, and I'm trying to draw a line that's parallel to, let's see here if I can do it, to the other vector. That's kind of parallel. And then from the other end, I'm going to draw another parallel line to the blue vector. The intersection between them should give me the resultant. So what you do, you draw the vector from the origin to the point of intersection that we found. That happens to be, let's see, negative 2 and 5. So my resultant has the form of negative 2 plus 5i. You know, you can sure check on that, because sometimes if you don't have a ruler or if you don't have a precise way of doing it, you want to check algebraically if that is correct. So because I was adding the vectors, you have 2 plus 3i, that was one part, plus negative 4 plus 2i. Now what you do, you want to make sure you add the real parts together, and then you add the I terms together, or simply said, the imaginary parts together. So let's do that. If you group 2 and negative 4, yeah, that gives you negative 2, and that's part of your x-coordinate, or a. And then if you look at 3i plus 2i, that gives you 5i, and that's part of your y-coordinate on this graph, or part b. Hence, the number, the complex number that we got, negative 2 plus 5i, it is indeed the result, and I'm going to call it r. So it checks out to be correct based on the graphic method that we did. Now let's talk about the standard form, or the polar form. I'm sorry, let's talk about the polar form of a standard a plus ib. So now, if you are looking at the graph that we had above, I'm going to draw a mini graph right above here somewhere. So look what I'm going to do. I'm going to draw my axes. Here's y and here's x. Remember, on the x, I am representing the a component, right, the real one. And on the y, I'm representing that b part, which is the imaginary one. So essentially, by drawing a vector that starts in the origin, let's say this is my vector, and I am actually looking at the coordinates. This coordinate here is x. This coordinate here is y. This vector that I just drew is nothing else but x plus I, y. Or you can say x plus y, I, either way. Very good. Now, if you're looking at the angle that is formed between the vector and the x-axis, that is your angle theta. So now, by sitting in a triangle here, yeah, either one of these triangles, you have to think, what is each coordinate? Well, if you do sinus of x, sinus of theta, right? Sinus of theta is opposite, which happens to be y, right? Opposite over hypotenuse. Yeah, so the hypotenuse is the r, is that part of the, I would say, the radius, right? Or the vector, let's say, resultant, if you may want to call it that way. So now, if you look at it and you pull out from there the component of x, well, then it comes out that x is r cosine of theta. Similarly, you look in a triangle on the y direction, and you will determine that y is r sine of theta. Why? Because sine of theta is y over r. But who is r? If you look here on a triangle, yeah, r is the hypotenuse. So this was x, and this was y. So the hypotenuse, applying the Pythagorean theorem now, you get that that is square root of x squared plus y squared. So that's great. You have just about everything you want to know about the vector except theta. There are many problems in physics where you will have to determine what angle does your vector form with the horizontal axis. So assuming that you actually know the components of the vector, which are y and x, then you can simply say, okay, well, tangent of theta in the same triangle I draw there, it is y over x, which is opposite over adjacent. Obviously, one condition that has to be met is that x is different than 0, because you can divide by 0, right? It gives you an error of infinite. Now, having said that, we have everything we need to write the polar form. What is a polar form? It's a way to express the number x plus y or yi in this format, r parentheses cosine of theta plus I sine of theta. Well, how did we get that? Well, if you look, x was nothing else but r cosine of theta plus I parentheses y is r sine of theta. Then you factor out factor out r, and then what's left is your new expression for writing the number, the complex number. So it's r parentheses cosine of theta I sine of theta. And it can be abbreviated in a very strange way, right? You take just the initial of all of that. It can be abbreviated as r, that's part of the beginning. Instead of cosine, we're going to say a c. And then we're going to put a I, S, C-I-S, theta. So that's the short version of writing the same thing. Now, in other words, r parentheses cosine of theta plus I sine of theta is the same thing as r c-I-s of theta. Same thing. So now let's apply all of this and do an example. So what you have here, you have a polar form, which is given to you like so, and they ask you to put it into a regular form, rectangular form, which is standard form, right? So when you're going to go ahead and go to standard form, what you need to have in mind that you have to put in a format x plus yi or a plus bi, something like that, right? So let's identify what we are given here. If you look this 10 is your r. Obviously, your 135 is your theta. And then you have all the other components to look of what this represents. This is nothing else but 10 CIS of 135. This is the same polar form, but you would like to actually write this in a standard form. So what you are to do is use the unit circle. So by using the unit circle, you will find out that cosine of 135 degrees, which is in Q2, right, quadrant 2, is a multiple of your 45. So this is negative root 2 over 2. Similarly, you're going to find out that sine of 135 degrees, it's the same thing since it's a multiple of 45, but it's positive, being in quadrant 2, square root of 2 over 2. Good, so now I go and plug these values in. So I'm getting 10 parentheses, negative root 2 over 2, plus I root 2 over 2. Now what can I do here? I can distribute the 10. Yeah, so 10 multiplies is every term from the parentheses. And then you simplify, right? 10 divided by 2 is 5. So you get negative 5 root 2. So that is your real part, plus 5I root 2. It is always preferable to put a square root at the very end. So this is the form. So you have, here's your x, which is negative 5 root 2, and your y is simply 5 root 2. So now you have the number that was given to us in polar form. Now we have it in standard rectangular form. So this is one way to do it. Let's go over the steps a little bit, particularly if you have to convert. So again, when you do this conversion, you can go both ways. What if you go from a rectangular to trig form, right? Which is you go from x plus yi or a plus bi to r cis of, cis of theta. So what if you go to that? So the first they tell you, okay, scratch the graph of number x plus yi or a plus bi. So you're going to put that in a plane. You're going to sketch that, make a drawing and all that. Once you do that, you can find the hypotenuse, right? So the hypotenuse is r, which is square root of x squared plus y squared. In physics, we actually use x and y as a sub-index. So you can say r is equal to square root of r index x squared plus r index y squared, which makes a whole lot of sense because you're talking about the vector r. But if you have 100 vectors, well, each one is going to have an x and y component, and that is y. Okay, now then find the angle theta by using the tangent. So you're going to use here tangent of theta is nothing else but equal to y over x, right? If you really think about it, that is opposite over adjacent. Remember that x has to be different than 0 for this to exist. Once you are done, then make sure you, by the way, you look at the quadrant very clearly. It will be very important to determine the correct signs. Okay, so let's do the next example. Example 3 kind of broke down here on the end of the page, but you're going to have to convert from rectangular to trig form, to polar form. So look what they give us. So we have here x plus bi. So if you identify x is 8 and y, let me stay consistent here. I say y and I wrote b. So x plus yi, and so y is negative 8. Now you can actually determine the quadrant. As you can see, x is positive, y is negative. This is quadrant 4. So I'm going to make a little sketch right here. And I know this is going to be in a square format because they are both 8s. So here's 8 and negative 8. And if you are to draw the vector, remember from the origin to the endpoint, this one has the coordinates 8 and negative 8. And now you're going to be looking for your angle theta. It doesn't matter which way you're going to go, you're going to have the same tangent and the same sinus being in this quadrant. Remember, this is your real part on the x-axis, and on the y-axis, That's your imaginary part. So remember to follow the steps here, kind of stay on track. So determine the hypotenuse r, or the resultant, which is square root of x squared, which is 8 squared, plus negative 8 all squared. Now if you do the math here, right, you get 64 plus 64, that is square root of 128. This is not a perfect square, but never leave the answer unsimplified. So because it's 64 times 2, 64, square root of 64 is 8. So you end up with 8 root 2. So keep up in the back burner. You're going to need it at the very end to write the trig form. Good. The next step is to find theta. So now tangent of theta, which is y over x, is negative 8 over 8. So that gives you negative 1. Now, because tangent of theta is negative 1, your reference angle is, so the reference angle is 45 degrees, but this is in quadrant 4. So theta belongs to Q4. 4, okay? Meaning that you do 360 minus your 45, you get nothing else but theta equals 315. So pay attention to that, because that gives you what kind of reference angle you should use. So now you have all the data. You have r and you have theta. So you can write this in multiple ways. So essentially 8 minus 8i becomes nothing else but r, parentheses, cosine of the new theta plus sine of the new theta. So my r was a root 2, parentheses, cosine of 315 plus I of sine of 315. If you want to use the short version, you're going to write 8 root 2 cis of 315. So be aware that sometimes they may give you the long format or the short format, and you're going to be allowed to answer either way. So pretty straightforward. Pay attention to your steps and pay attention to your algebra. Now you're dealing with negative 15. Negative 15 is nothing else but essentially a real number, right? And any real number can be written as a complex number if you make that b or y equals to 0. So this can be x, which is negative 15, plus 0i. Same thing, right? Multiplication with 0 is 0. Meaning that now I can find my r, since I identified that my x is negative 15 and my y is 0. So essentially r is square root of negative 15 all squared. And you know the all squared part takes care of the negative, that becomes a positive, plus 0 squared. Okay, cool. So that becomes square root of 15 squared, which is 225. And since it's a perfect square, this is 15. So I identify my r. The next step again is to identify the theta. So if you really look at it, this theta has to be theta, tangent of theta. It is y over x, and y was 0, and x is negative 15. 0 divided by any number is 0. So if you look at your unit circle, where is theta equals to 0? So theta equals to 0 for 180 degrees. It's kind of like how I looked here and I said tangent of theta is negative 1. You can actually use the inverse tangent, right, to find that theta. And you can say theta is arctangent or tangent minus 1 of whatever value you got. Then you put that in a calculator and you will get the angle in degrees, assuming that your calculator is set in degrees. So now we can write that negative 15 can be written as 15 parentheses cosine of 180 plus I sine of 180. Or if you want to use the short form, is 15 cis of 180. And you know, feel free to actually double check, right? If you look on a unit circle and you say, well, wait a second, sine of 180, it is 0. So that whole term that contains I goes away. All right, so this is how to use this application. So we're going to look at the next example. This is converting between trig and rectangular form using calculator approximation. So for here, you definitely want to have your calculator ready. Please make sure you set your calculators in degrees. In degrees. Why? Because these forms that we are talking about contain, like for example in part B, where you have -7 plus 2i, you have to get r, parenthesis, cosine of whatever angle theta will be, and that's in degrees, right, plus I sine of theta. Okay, so let's look at the first problem actually. So here, the first thing you want to do is depict these particular values. You want to depict those using a calculator. So if you use your calculator, I actually kept a bunch of decimals. I'm going to write them all. So 7 parentheses. Now I'm getting cosine of 205, negative 0.906, 307, 787. Okay, so that's for that cosine plus I, and now it's time for sinus. Well, that sinus also becomes negative 0.4226, 182,617. I kept as many decimals as possible, and then I closed the outside parentheses. So these are the approximations that you are asked to use your calculator for. Then you have to multiply this 7 with each term of the parentheses. And by doing so, we get the following answer here. Negative 6.3442. They don't tell you how many decimals, do they? They don't, okay. I like to keep 4 decimals, either 4 or 2. Sometimes some of your homework will specify how many decimals you need to keep, so just go with what it says in the instruction. If it doesn't enter 4 decimals, you're going to be fine. Minus 2.9583. You know, you may want to check sometimes what I'm doing here. If we are to round this, so we're going to have 6. That's rounded to 1 decimal, negative 6.3 minus 2.96 or 2.9 I. I guess I'm going to put a 5 here then. Either way. So that's how you do these conversions. So you are in a polar way and you came up to a standard way, this one. Let's see part B. Part B is exactly opposite. So you start right with the rules that we said before. You identify your x and y, or a and b. Here's your x is -7. Here's your y is +2. So by identifying them, then you can calculate your r. R will be square root of -7 squared plus 2 squared. So that's what? 49 plus 4. So that's square root of 53. And that's one of those that you cannot really break down. So we're going to leave it in that format. There's nothing that comes out from underneath that square root, so you cannot simplify it any longer. Then we're going to look for tangent of theta. We need to find the angle in order to write it in a polar form. Remember, tangent is the y component over the x component. So my y component is 2. My x component was -7. So now if you put, this is a negative number, right? If you really look at your unit circle, is in theta, and not only that, you look at x and y, right? So let me make a quick drawing here. So I just try to fit them all in here. So x is -7. So let's say here's your -7 on the x direction. And on the y direction, I have 2. So the intersection between them forms the end or the tip of your vector, and it starts in the origin, this pretty much tells me that my angle is in quadrant 2. So this vector I represented is nothing else but has the coordinates of -7 and 2 in a complex plane. So that was x and that was y. And means this is -7 plus 2i. So what am I looking at here? So I find out that theta belongs to Q2. And so because of that, you need to look at what is your reference angle, right? Because if you are using a calculator right now and you do tangent -1 of -2/7, that will give you your theta. So if you do that, you get about 15 something, 15.95. But see, 15.95 belongs to Q1. So theta is nothing else but 180 minus 15.95. And again, this is given by the x and y coordinates, which tells you exactly which quadrant you are in. And this is 164.05. So kind of a weird angle, but that's what they want you to use calculators, not necessarily the unit circle. So how can I write my number? So I can say that -7 plus 2i can be written as r, well, r was square root of 53, parentheses, cosine of 164.05 plus I sine of 164.05. So this is great. You can write a short form of it, square root of 53 CIS of 164.05. Either form is correct, represents the same number. If you go now in reverse, starting here, going backwards, you will get these numbers, -7 plus 2i. If you start with developing, hey, how much is cosine of 164.05? Okay, the last theme of this lesson is a very interesting one. Has to do with fractals. And you're going to ask yourself, what exactly are fractals? Well, fractals, I want you to imagine if you remember when you were a kid and you look into a kaleidoscope, right? So when you look into a kaleidoscope, you have all of these points that they keep moving and that forms these geometrical patterns, and they have all sorts of axes of symmetry, okay? So I will write here kaleidoscopic effect. In reality is a function. This Julia set, which is part of fractals, is nothing else but a very complex function, right? And it has certain properties. And you're going to learn more. It has to do with Riemann series. And if you have three numbers of, that they are in the same plane and they move, how do they move? That's the idea behind it. So now, if we are looking at this, I think I had a, not so sure now, but I think I had a little video here. Here's something called the animated Julia set. So essentially, if I move the points, see, I'm just clicking on a screen at different points, and you can see how the behavior is of such a set. And if I move back in, it will form a different perspective of it. So it's nothing else but I'm moving different sets by moving 3 points at a time. Why 3 points? Because 3 points define a plane. Yeah. So let's go back to, you know what, let me copy this. And then I'm going to put it actually in here for you. Let me see if I can say on text and put it in here and paste it. So you should have now that, let me see, return. Oh, I don't need to press return. All right, so we are good to go. At least now you have this particular link straight on the handout. And you can play with that too and just see how that works. So remember, this kaleidoscopic effect is very fun to watch, and typically is done with pieces of glass or confetti, anything that has different shapes and colors, and it's easy for you to see. But remember, a Julia set is nothing else but a complex number. It's a function, and it has certain properties. So for this particular level, we are just going to look, hey, is a fractal that is called a Julia set shown in a picture? Well, they show you one of them, to determine whether this complex number in this Julia set could be anywhere, right? We don't know where it is exactly. Perform the following sequence. So we're going to take that z and you're going to square it and then subtract 1. Then the next step, you're going to take the previous z, which was z squared minus 1, right, which was this one. And again, you're going to square it and say minus 1. And you're going to keep doing that. Now you're going to take the whole thing here from the second step. You're going to square that one and subtract 1. And every single time you get a new number. Well, what's the important part here? The important part is that any of the resulting complex numbers exceeds 2. If any of this happen, then the complex number is not a Julia set. So the bottom line is whatever you get when you do these transformations, you have to get something that is less than 2. If it's less than 2, you know it's a Julia set. If it's not, if it does not belong to the Julia set. In other words, it does not belong to the transformation you see in front of your eyes. As you can see, this is a transformation that at least I can identify 2 axes of symmetry, right? On a vertical and horizontal. But in reality, it has more than that axis of symmetry. All right, so let's look at our numbers. The first number given here is z equals 1 minus 1i. That is my z. So the first step I have to look at is I have to perform this, z squared minus 1. Well, let's do it. So z squared in my case, minus 1. Well, z squared is 1 minus 1i. This is all square, and then minus 1. I'm going to color this minus because that belongs to the performance of the operation, algebraic operation for the Julia set. Good. What is on the first part right here? Well, that's a binomial square, right? Remember that one? Let me rewrite this square. So that's a minus b all square, a squared minus 2ab plus b squared. So let's apply that rule. So this becomes first one square minus 2 times the first one times the second one, which is still 1. In this case, the formula already takes care of the signs, plus or minuses, that is. And then I, right? That's the second one, 1i. And then plus the second one squared. Well, is 1i all squared. And then we have the minus 1 that belongs to the sequence that I have to check if it's going to be less than 2. Now let's do the algebra part. 2 times 1 times 1, that's negative 2, so negative 2i. And then 1i squared, so I'm going to put a plus right there. But remember that I squared is negative 1. So negative 1. Negative 1 times 1 is still negative 1, and then minus another 1. That's your 1 that belongs to the sequence. All right. So now let's see who reduces out, simplifies out. So 1 and negative 1 goes away. I am left here with negative 1 minus 2i. So now the question is, how do you perform the next step to check if indeed the number does not belong to the Julia set or does belong to the Julia set? Remember, you need to check your R, right? You have to check my R has to be at least less than 2 in order to write my new number in an a plus or x plus yy format, or to move it into a angle, I would say, in this case. So if I'm looking here, is this R is also called either resultant or modulus. So R equal the resultant. In other textbooks, this is called the modulus. I believe your textbook has both. So who is r? Well, r is square root of my x squared plus y squared. Yeah, so I'm going to look. My x is 1. So this is 1 squared plus, is negative 1. Yeah, I'm looking in the wrong part here because I'm looking at this number that I have to prove that belongs to the Julia set. That's the one I'm looking at. So now plus negative 2 squared. Well, let's do the math here. Negative 1 squared is 1, negative 2 squared is 4, 4 plus 1 is 5. So look what I'm getting. R is equal square root of 5. At this moment, if square root of 5, which you know is a number greater than 2, right? So let's see here. I think it's, where is it? Yeah, 2.23. So this is greater than 2. You're going to stop right there. You know that this is not going to belong to a Julia set. Yeah, so R is greater than 2. So it is not a Julia set. Or you can say it does not belong to the Julia set. Let's do the next one. So in the next example that we have, we are looking at original z is that. Then you need to do, as we did before, you need to go to the next step. So the next step is z squared minus 1. So let's go ahead and do that. Z squared minus 1, that is negative 1 plus 0i all squared minus 1. I'm not going to keep changing colors. You know that that minus 1 that came into place is from doing the performance of calculations for the Julia set. Good, so we are dealing again with a binomial square. So what do you get? Negative 1 all squared plus 2 times negative 1 times 0 I, and then the last one here is plus 1 squared, and then minus 1 that was already present. All right, so let's see what do we get here. This 1 squared with a negative, right, it is 1. This part right here is 0. Then you have a plus 1. Oh, my bad. This was a 0, 0. Yeah, I missed it. So the last part is second square, right? So 0i all squared. Well, it doesn't matter what we do here. That's still a 0. And then minus 1. All right. So what am I getting here? I'm getting a 0. Well, that is less than 2. Even if I start writing it in a CIS format, it's still less than 2. That means I can continue. Yeah, so now I'm going to take my new z that I got and do that one, right? So z squared minus 1, which is the original one, all squared minus 1. So I'm going to write that down. D squared minus 1, which is my original one, squared minus 1. Well, my number now got to be 0. So it's 0 plus 0i, essentially. So that becomes 0 squared minus 1. So this is negative 1. This is also less than 2. So even if you do the modulus, it's still less than 2 if you want to write it as a CIS. That means I can continue. So I'm going to take again my original number, which was z squared minus 1, all squared, and then minus 1 is the number above, right? All squared, just like so. And then minus 1. I'm in step 3 right here, right? So I'm doing this part right here. Yeah. So be very careful, you know, it's just a little tedious work, but if you pay attention, you're going to be fine. So if I am looking at this guy, this part right here is negative 1. So you get a negative 1 squared minus 1, and I'm getting a 0 again. So this is awesome. This is also less than 2. That means I can continue. So I don't think I have to continue because every single one of them, it's probably going to repeat. It's going to be 0, negative 1, 0, negative 1, 0, negative 1, and so forth. So these points will always move. That means that if you look, this results that the original z equals, what was it in the problem right here? Negative 1 plus 0i, negative 1 plus 0i is a Julia set. In other words, belongs to a function that will move points that will be in accordance to how the Julia sets function work. And you don't do this here, but I think it's fun to kind of know that it exists. And again, as I say, the best effect is a kaleidoscopic effect, where you have all the symmetries in a world for different things and how they move. It's a behavior. It's actually the study of advanced dynamics. That's what it is. And fluid dynamics, whether it's fluid, air is also a fluid, and even gas dynamics, right? Anyways, that's it. This is the lesson for today. And thank you. I hope you found it helpful.